Today's video is about magnetic levitation, and what we're going to do is levitate this aluminum knob. It's sort of a threaded knob that probably came from a tripod or some sort of scientific instrument. I really don't know where I got it, but the good thing is it's a disc of aluminum, and we're going to levitate it above this old transformer core that we've been doing other experiments with. So, well, let's get on with it. So the demo is really quite simple. We're going to take the core, which you've seen, and attach it to this variac. And I've made a couple of little metal things to hopefully easily attach the wires together, like that. And what we're also going to do is use this ammeter so we can see how much current is flowing. And I think we're ready to go. So, to make it work a little bit more obviously, we'll hold it in place with a plastic pen and take a look at what happens. Kind of neat, isn't it? So, how does this work? What causes this thing to levitate? Well, the first hint is that, well, this disc here is getting quite warm, and that means there's been a big current flowing through it. And what would cause that current? Well, it's the magnetic field from the transformer. Now, when we looked at current transformers a while back, what was pretty obvious at that point is when you have a shorted coil in a transformer, such as the sense winding in a current transformer, it forces the changing magnetic field through the core to be zero. Well, this floats above the core, so there's clearly still a magnetic field here, but it does ensure that any magnetic field going through our aluminum disc is zero. And it does it by having a current flow in the opposite direction as the current flowing in the exciting core on the transformer. And what that essentially means is, well, you could consider this single one-turn winding to be producing a magnetic field that is opposite to the magnetic field coming from the core, and, well, opposite fields repel, so it repels and hangs around somewhere up here. The other way to look at it is the current in our aluminum disc goes in the opposite direction to the current in the transformer windings. And you might remember another video we looked at, which was how wires carrying current in opposite directions repel. Well, that's another way to look at the mechanism for levitation. And there is one more way, and that is, because this is shorted, we've said the magnetic field can't actually enter the aluminum. Well, I sort of lied about that one. That would be true if this was essentially a superconductor, but it's not, or I wouldn't be holding it like this. Because it's a piece of aluminum that has some resistivity, the magnetic field does penetrate a bit, and it produces a current that penetrates in the aluminum, and it sort of begins to drop off with distance, and that distance is known as the skin depth. And for a 60 hertz field in aluminum, it's about a centimeter, or about the thickness of this disc here. And what that really means is, well, the magnetic field starts dropping off as it penetrates the disc, and when we push the disc down, it's squishing all the flux from this core into a narrower and narrower space. And that actually increases the energy in that magnetic field. And, well, things don't like having their energy increased, and that's what causes a repelling force. So there are really a number of ways you can look at it. In fact, it's probably a little bit more complicated than any one of them because there are phase shifts. This is actually AC current. The phase of this isn't quite what it should be because of the resistivity in here. And so you also have to deal with the fact that this field is varied over here and that we're up here only affecting the top of the field. The bottom line is the calculation gets quite complicated and you probably need to do some sort of computer analysis using finite elements to figure out exactly what's going on. But as I just showed you, we can get a good sense of what's causing the repelling force. So that's how magnetic levitation works. It was a fun video to do. I hope you enjoyed it. See you next time.